Right now, as you watch this, trillions of ghostly particles are streaming through your body every single second. They are passing through the floor beneath you, through the entire Earth itself, as if it weren't even there. These are neutrinos, the universe's most elusive and enigmatic travelers, born in the hearts of stars, in cataclysmic supernova explosions, and in the most violent cosmic events imaginable. But their greatest secret isn't out there in the distant cosmos. It's a faint cosmic whisper that has been traveling since the very dawn of time itself. This is the Cosmic Neutrino Background, a relic sea of particles left over from the Big Bang, and it holds mysteries that could completely shatter our understanding of everything. We've all seen the famous map of the cosmic microwave background, the afterglow of the Big Bang that paints the infant universe in faint microwaves. It's a cornerstone of modern cosmology. But what if I told you there's an older, far more ancient snapshot of the universe, one that was created a mere 1 second after the birth of everything? While the microwave background shows us the universe at 380,000 years old, the cosmic neutrino background captures it in its very first second of existence. This is a view into a universe so young, so unimaginably dense and hot, that the laws of physics as we know them were only just beginning to take shape. It's a direct line back to the creation event, and it's been bathing the cosmos unseen and almost undetectable for over 13 billion years. Yet, for all its profound importance, the cosmic neutrino background remains the final, great, uncharted frontier of cosmology. It is a treasure trove of secrets, and within its faint signal lie 25 profound mysteries that challenge our most fundamental ideas. Why is there more matter than antimatter? What is the true nature of dark matter? Does our standard model of particle physics need a complete overhaul? The answers are locked within these ancient neutrinos. In this video, we will journey into the heart of this incredible mystery, exploring these 25 cosmic puzzles one by one. We'll uncover why detecting this background is one of the hardest challenges science has ever faced, and how succeeding could rewrite the story of our universe. This isn't just a story of particles, it's a story of our quest to understand our own origins, a journey to listen to the faintest echo of the beginning. So let's begin. Let's dive into our very first mystery, a puzzle that stands as a formidable gatekeeper to all the others. Why is this ancient neutrino background, this sea of particles that fills the entire cosmos, so impossibly difficult to detect directly? The answer lies in the very nature of the neutrino itself. These particles are the ultimate introverts of the subatomic world. They barely interact with anything at all. Think about the light from your screen, which is made of photons. Photons interact with matter through the electromagnetic force, which is why they hit your retina and allow you to see. But neutrinos are different. They are immune to both the electromagnetic force and the strong nuclear force that holds atomic nuclei together. They only feel two of the universe's fundamental forces: gravity, which is incredibly weak on their tiny scale, and the weak nuclear force, which, as its name implies, has an extremely short range and is, well, very weak. This means a neutrino can pass through light years of solid lead without even slowing down. It's this ghostly quality that makes capturing one an event of sheer luck. Now consider the technology we use to catch neutrinos today. Facilities like the Super Kamiok and detector in Japan are monumental achievements. Super K is a colossal tank buried deep underground, filled with 50,000 tons of ultra-pure water. It's designed to wait for the incredibly rare moment when a neutrino, traveling from the sun or a distant supernova, actually bumps into an atomic nucleus in that water. This collision creates a faint flash of light which is picked up by thousands of sensitive sensors lining the tank. It's an incredible feat of engineering. But here's the catch: these detectors are built to see high-energy neutrinos, the ones coming from powerful astrophysical events in the present-day universe. The cosmic neutrino background is entirely different. These are the universe's first neutrinos, and they have been traveling and losing energy for over 13 billion years. They are now incredibly cold and slow, possessing only a tiny fraction of the energy of the neutrinos we currently hunt. They are the quietest whisper in a universe filled with cosmic shouts. To put this challenge into perspective, imagine trying to hear a single, specific conversation happening on the other side of the planet, but you're standing in the middle of a roaring stadium during the final moments of a championship game. The crowd's roar represents the constant barrage of high-energy neutrinos from the Sun and other cosmic sources. The faint, distant conversation you're trying to hear is the cosmic neutrino background. Our current detectors are simply not sensitive enough to pick out that one quiet voice from the overwhelming noise. Detecting the CNUB directly is considered the holy grail of neutrino astronomy because it would require a detector of almost unimaginable scale and sensitivity, one that could perhaps use an entire planet as a shield against other particles, or employ a new, revolutionary technology we haven't even conceived of yet. It's a challenge that pushes the very limits of our ingenuity, a testament to the fact that the universe's deepest secrets are not given up easily. This brings us to our second great mystery, one that asks a surprisingly simple yet profoundly important question. How cold is this ancient sea of neutrinos? You might think that something as fundamental as the temperature of a relic from the Big Bang would be a known quantity, but it remains a number we have only theoretically predicted, not yet measured. And the story behind this predicted temperature is a direct consequence of the universe's explosive early expansion. According to our best models, the cosmic neutrino background should have a temperature of approximately 1.95 degrees above absolute zero. That's significantly colder than the more famous cosmic microwave background, which sits at a relatively warm 2.725 Kelvin. But why the difference? The answer lies in a pivotal event that happened when the universe was just a few minutes old. To understand this, we need to rewind the cosmic clock. For the first few 100,000 years, the universe was a seething, opaque plasma of light and matter. Photons, the particles of light, were constantly bouncing off free electrons trapped in a dense fog. Meanwhile, the neutrinos, having stopped interacting with anything else a mere second after the Big Bang, were already streaming freely through this hot, dense soup. Then a cosmic milestone occurred, recombination. As the universe expanded and cooled, electrons and protons finally combined to form the first neutral atoms. Suddenly, the fog lifted. The photons, which had been trapped for so long, were finally set free. This moment of liberation is what we see as the cosmic microwave background. But crucially, something else happened at that very instant. The energy released when all those electrons and protons combined into atoms injected a tiny bit of extra heat into the photon field, warming it up. The neutrinos, having decoupled much earlier, missed this entire party. They received no extra energy boost. They simply continued to cool as the universe expanded around them, preserved in their more primordial, colder state. This is why a precise measurement of the cosmic neutrino background's temperature is so much more than just recording a number. It is a direct test of the physics of the universe's very first second. The prediction of 1.95 Kelvin isn't a guess. It's a precise calculation that emerges from the well-understood thermodynamics of an expanding and cooling gas of particles. If we could measure the temperature and it matches this prediction, it would be a spectacular confirmation that our understanding of the universe's infancy is correct. It would validate our models of how particles behaved under conditions of unimaginable density and heat. But what if the measurement is different? A deviation, even a small one, would send shockwaves through cosmology. It could indicate that there are unknown physical processes at work, perhaps a previously undetected type of particle that interacted with neutrinos after they were thought to have decoupled, or even a flaw in our fundamental understanding of gravity and expansion. The exact temperature of the CNUB is a key that could either lock the standard Big Bang model firmly in place or unlock a door to a completely new physics waiting to be discovered. This third mystery takes us deeper into the identity of the neutrino itself, confronting us with a fundamental question we still cannot answer. What is the true weight of these cosmic ghosts? For a long time, the standard model of particle physics assumed neutrinos were massless like photons, but groundbreaking experiments in the late 20th century confirmed that neutrinos do, in fact, have mass. They oscillate or change flavor as they travel, a quantum phenomenon that is only possible if they have some small amount of mass. This discovery was Nobel Prize winning, but it opened a Pandora's box of new questions. While we know they have mass, we have no idea what their actual masses are, or, just as crucially, how those masses are ordered relative to each other. This brings us to the puzzle of the mass hierarchy. Think of the three known neutrino flavors: the electron neutrino, the muon neutrino, and the tau neutrino, not as having fixed weights, but as unique quantum mixtures of three underlying mass states. Let's label these fundamental mass states as 1, 2, and 3, with 1 being the lightest and 3 the heaviest. The normal hierarchy is what our intuition might suggest. The electron neutrino is most closely tied to the lightest mass state, creating an ordering where the masses increase steadily, much like the masses of the electron, muon, and tau particles themselves. The inverted hierarchy, however, turns this upside down. It proposes that the electron neutrino is associated with one of the heavier states, resulting in a kind of upside-down pyramid of mass. Determining which of these scenarios is correct is one of the highest priorities in particle physics, because the answer has profound implications for theories that seek to go beyond the standard model, potentially pointing us toward a grand unified theory of everything. This is where the cosmic neutrino background becomes an indispensable tool. While particle accelerators here on Earth struggle to distinguish between the two hierarchies, the cosmos itself may have already performed the experiment for us. The key lies in gravity's subtle influence over billions of years. The cosmic neutrino background isn't just a uniform sea. Its distribution has been sculpted by the gravitational pull of the universe's large-scale structure. The vast cosmic web of galaxies, galaxy clusters, and dark matter halos. Heavier neutrinos would have been more strongly attracted to these dense regions of space. Over cosmic time, this would have caused a slight clumping, an enhancement in the density of the neutrino background within and around these massive structures. A detection of the CNUB would allow us to map this faint clustering. If we could measure the pattern, we would essentially be reading a history book written by gravity. A stronger clustering signal would point toward the inverted hierarchy, because it would mean the neutrinos have, on average, a higher mass, making them more responsive to gravitational tugs. A weaker, more uniform distribution would support the normal hierarchy. This gravitational imprint is something that can only be seen in the relic neutrino population. The high-energy neutrinos we detect from the Sun or supernova are moving far too fast for gravity to have had any meaningful effect on their paths. They are cosmic speedsters. But the neutrinos of the cosmic neutrino background are slow and cold. They have been traveling for so long that even the faintest whisper of gravity has had 13.8 billion years to leave a detectable mark on their journey. Resolving the mass hierarchy isn't just about filling in a blank in a table of particle properties. It's about understanding the neutrino's role in the evolution of the cosmos itself, from the formation of the largest structures to the ultimate fate of the universe. So the question of which hierarchy is correct becomes a compass pointing toward the next great theory of physics. The standard model, for all its success, is incomplete. It cannot explain why neutrinos have mass at all, much less how that mass is ordered, but the cosmos, through the relic neutrino background, offers us a clue. The incredibly small masses of neutrinos are a puzzle in themselves. Why are they billions of times lighter than the electron, the next lightest particle? One of the most promising explanations is a concept called the seesaw mechanism. Imagine a playground seesaw. On one end, you have a very heavy child, and on the other, a very light child. For the seesaw to balance, the light child has to sit much farther from the pivot point. In particle physics, the heavy child is a hypothetical, incredibly massive particle that has never been seen. The light child is our familiar neutrino. The seesaw mechanism elegantly explains the neutrino's tiny mass as a natural consequence of this partnership with a super-heavy counterpart. But here's the crucial part. Different versions of the seesaw mechanism, which are embedded in various grand unified theories, predict different mass hierarchies for the light neutrinos we observe. A confirmed measurement of the hierarchy from the cosmos would act as a filter, instantly ruling out entire families of theoretical models and telling us which path toward a deeper, more complete theory of nature is the right one to follow. This connection is staggering to contemplate. By mapping the faint gravitational whispers in a sea of particles from the Big Bang, we could be testing ideas about energy scales 1 trillion times higher than what our most powerful particle colliders can ever achieve. It's as if the universe itself ran a monumental experiment in its first instant, and the results are encoded in the travel history of these ancient neutrinos. The implications reach even further, touching upon one of the most profound symmetries in nature, matter-antimatter symmetry. Our existence is a testament to a cosmic imperfection. During the Big Bang, matter and antimatter should have been created in equal amounts, annihilating each other perfectly and leaving behind a universe of pure energy. The fact that we live in a cosmos filled with galaxies, stars, and planets means that a tiny asymmetry must have occurred, allowing a small surplus of matter to survive. This is known as baryogenesis. The physics of neutrinos, particularly a property known as CP violation, is a leading candidate for creating this imbalance. The degree of CP violation, however, is intimately tied to the mass hierarchy. Knowing the ordering isn't just a technical detail. It directly influences the predicted efficiency of neutrino-driven processes that could have tipped the scales in favor of matter in the early universe. The inverted hierarchy, for instance, might allow for a much stronger matter-generating effect than the normal one. Therefore, unlocking the secret of the neutrino mass ordering is not just about particle physics. It's about answering the fundamental question of why anything at all exists. Now we arrive at a mystery that truly stretches the limits of our imagination, asking what secrets are preserved within this fossil from the very first second of time. The cosmic neutrino background is not just an old signal. It is the oldest possible picture of our universe, a snapshot taken an almost incomprehensible instant after the Big Bang. To grasp the significance of this, let's compare it directly with its more famous cousin, the cosmic microwave background. The CMB is our view of the universe at the tender age of 380,000 years. That might sound ancient, but in cosmic terms, it's like a childhood photograph of the cosmos. By that point, the universe had already expanded and cooled enough for atoms to form, allowing light to travel freely for the first time. It's a monumental moment, but it's not the beginning. The CNUB, on the other hand, captures the universe in its true infancy at just 1 second old. This is a universe that is almost indescribably different from anything we know. At that moment, the entire cosmos was a searingly hot, incredibly dense soup of fundamental particles, a plasma so thick that even neutrinos, which can pass through planets, were trapped within it. They were constantly interacting with protons, neutrons, and electrons. Then, as the universe expanded and its temperature dropped past 10 billion degrees, something pivotal happened. The neutrino fog lifted. The density of the universe had decreased just enough that neutrinos stopped colliding with other particles. They decoupled, flying free in every direction, and have been traveling in near-perfect straight lines ever since, their paths virtually untouched by anything they encountered over the next 13.8 billion years. This means the properties of the cosmic neutrino background, its temperature, its distribution, its very texture were set in stone during that first second, preserving a pristine record of the universe's condition at that exact moment. So, what information is locked within this ancient fossil? It holds the keys to understanding the physics of the highest energies. The first second was an era when all the fundamental forces of nature, electromagnetism, the strong and weak nuclear forces, and gravity, were likely unified into a single super force. Today, we can only theorize about what this grand unification looked like, but the CNUB is a direct messenger from that epoch. Its detailed structure could contain subtle imprints of processes that occurred when the forces were splitting apart, phenomena that are far too energetic to ever reproduce in a laboratory on Earth. Furthermore, this neutrino sea can tell us about the composition of the primordial universe. Just after decoupling, the cosmos was dominated by a bath of radiation photons and neutrinos that dictated its expansion rate. The presence and behavior of these relic neutrinos played a critical role in determining how fast the universe grew during its first few minutes, which in turn governed the nuclear reactions that forged the first atomic nuclei, hydrogen and helium, in a process called Big Bang nucleosynthesis. Any deviation we might find in the CNUB from our theoretical predictions would be a direct signal of new physics, perhaps pointing to the existence of unknown particles or extra dimensions that influenced the baby universe. The contrast between the two backgrounds is stark and revealing. The cosmic microwave background shows us the universe after it had already undergone immense evolution. It's a picture of the plasma just as it was cooling into atoms. The cosmic neutrino background shows us the universe before any of that structure had a chance to form. It is a pure, unaltered relic from an era of pure energy, a time when the universe was too young and too hot for even the simplest atomic nuclei to exist. By studying both together, cosmologists can perform a kind of cosmic archaeology, comparing the infant universe at 1 second old with the same universe 380,000 years later. This allows us to trace the entire history of its expansion and cooling with unprecedented precision, checking our models for any inconsistencies. The CNUB is therefore more than just a fossil. It is the ultimate time capsule, carrying within its faint signal the untold story of the universe's very first breath. This brings us to one of the most profound questions we can ask. Why are we here at all? Why does a universe of matter, filled with stars, planets, and life, exist? According to our fundamental physics, it shouldn't. The Big Bang should have created matter and antimatter in perfectly equal amounts, and when a particle of matter meets its antimatter counterpart, they annihilate in a flash of pure energy. So, in a perfectly symmetrical universe, every last electron should have met a positron, every quark an antiquark, until nothing remained but a vast, empty sea of light. The fact that we are made of the matter that survived this cosmic cataclysm means that a tiny 1 in a billion asymmetry must have occurred, tipping the scales ever so slightly in favor of matter. This is the mystery of baryogenesis, and our fifth puzzle asks an incredible question. Could the humble neutrino have been the architect of our entire material cosmos? This is where the theory of leptogenesis comes into play, a compelling idea that directly implicates neutrinos in this cosmic crime of existence. The story begins not with the light neutrinos we detect today, but with their hypothetical, incredibly heavy ancestors that existed for a fleeting instant after the Big Bang. In many grand unified theories, these heavy right-handed neutrinos would have been born in the unimaginable heat of the primordial universe. They were unstable, and they began to decay almost immediately. The key to leptogenesis lies in the details of that decay. For this process to create the matter surplus we see, the decays had to violate two fundamental symmetries of nature. The first is CP symmetry, which, simply put, means that the laws of physics should treat particles and their mirror image antimatter counterparts identically. If a heavy neutrino decays to produce ordinary matter slightly more often than it decays to produce antimatter, that's a violation of CP symmetry. The second requirement is that this process must occur out of thermal equilibrium, meaning it happened so fast in the expanding universe that there was no time for reverse reactions to wipe out the newly created matter asymmetry. So, imagine this scenario unfolding in the first fractions of a second. Heavy neutrinos pop in and out of existence, decaying in a way that favors the production of leptons, the family of particles that includes electrons and neutrinos over antileptons. This generates a small initial lepton asymmetry. Through a complex series of interactions that involve the weak nuclear force, this lepton asymmetry can then be converted into a baryon asymmetry, an excess of the protons and neutrons that make up the atoms of our world. In essence, a small bias in the ghostly world of neutrinos could have been the seed from which all the visible matter in the cosmos eventually grew. But how do we test such a grand theory about the universe's first moments? This is where the cosmic neutrino background transforms from a fossil into a forensic witness. While the heavy neutrinos themselves are long gone, their legacy might be imprinted on the properties of the light, relic neutrinos that fill space. The specific way the CNUB neutrinos oscillate or mix with one another could reveal subtle clues about their massive ancestors. The degree of CP violation required for leptogenesis to work is directly linked to the mass hierarchy of the light neutrinos we observe today. If we can finally determine whether the neutrino masses follow a normal or inverted ordering, as we discussed earlier, we can severely constrain or even rule out entire classes of leptogenesis models. Furthermore, if the CNUB holds any surprises such as an unexpected distribution of flavors or a slight deviation from the predicted temperature, it could be a direct signal of these high-energy processes that occurred far beyond the reach of any earthly accelerator. The staggering implication is that by studying the coldest and slowest particles in the universe, we might be piecing together the story of how everything we see and touch came to be. The cosmic neutrino background is not merely a relic, it is a potential chemical fingerprint left at the scene of the universe's creation, a faint but indelible mark of the process that allowed a universe of something to emerge from what should have been nothing. Moving on from the grand question of our existence, we encounter a mystery that strikes at the very heart of the standard model of particle physics itself. For decades, we have known of three types or flavors of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. This three-neutrino picture is a cornerstone of our understanding. But what if it's incomplete? What if the cosmos is hiding a fourth, or even more, types of neutrinos that are so ghostly, they make the familiar ones seem almost sociable? This is the tantalizing possibility of sterile neutrinos, and the cosmic neutrino background could be the key to proving their existence. Sterile neutrinos are one of the most intriguing hypothetical particles in physics. Unlike the three active neutrinos we know, which reluctantly interact via the weak nuclear force, sterile neutrinos would be utterly aloof. They would feel only gravity, completely ignoring the weak force, the electromagnetic force, and the strong force. This makes them effectively invisible to every type of detector we have ever built, which rely on these very interactions to spot particles. You could have a sterile neutrino pass through a detector the size of a planet, and it would leave no trace whatsoever. So why do we even think they might be real? The evidence comes not from direct detection, but from a series of persistent and puzzling anomalies in experiments around the world. For instance, some experiments studying the flow of neutrinos from nuclear reactors have detected a curious deficit. The number of electron antineutrinos detected is slightly lower than our models predict. This discrepancy, often called the reactor anomaly, could be explained if some of the electron antineutrinos were transforming or oscillating into a fourth type of neutrino that our detectors cannot see, a sterile neutrino. Similar anomalies have popped up in experiments using intense radioactive sources and even in data from the Large Hadron Collider. Individually, each anomaly might be a statistical fluke or a measurement error. But collectively, they form a compelling pattern that suggests our three-flavor model might have a hidden passenger. This is where the cosmic neutrino background offers a completely independent and powerful test. The physics of the early universe is exquisitely sensitive to the number of light, active particle species present. Think of the infant cosmos as a tightly sealed pressure cooker. The more types of particles you have buzzing around inside, the higher the pressure and the faster the cooker expands. We can actually measure this early expansion rate by looking at the aftermath of Big Bang nucleosynthesis, the process that forged the first atomic nuclei. The observed abundance of light elements like helium and deuterium acts as a cosmic speedometer for the universe's first few minutes. The data strongly favor the existence of 3 light neutrino species, which is a fantastic confirmation of the standard model. However, the precision of this measurement leaves a small window open. The numbers don't completely rule out the possibility of a 4th neutrino, but if it exists, it would have to be different. It would have to be sterile, not contributing fully to the weak interactions that govern that era. A detection of the cosmic neutrino background would slam this window shut or blow it wide open. The energy density of the relic neutrino sea is a direct function of the number of neutrino species that decoupled a second after the Big Bang. If there were only 3 light neutrino types, the energy density would have a very specific predicted value. But if a sterile neutrino existed and mixed ever so slightly with the active neutrinos in the primordial fireball, it would have contributed to the energy budget of the universe, leaving a distinct signature in the CNUB's properties. This signature would manifest in 2 primary ways. First, it would alter the overall energy density of the background, effectively making the neutrino sea a bit richer and denser than expected. Second, and perhaps more importantly, it would leave a unique imprint on the cosmic microwave background. The gravitational influence of the cosmic neutrino background helped sculpt the faint temperature variations we see in the CMB. The presence of additional neutrino species would have changed how these cosmic structures formed. Planck satellite maps of the CMB are already so precise that they allow us to count the effective number of neutrino species with remarkable accuracy. Current results are perfectly consistent with 3, putting severe constraints on any sterile neutrino model. But the CMB data alone cannot completely resolve the issue. A direct detection of the CNUB would be the ultimate arbiter. It would give us a perfect census of the relativistic particles present in the universe's first second. Finding exactly the energy density we expect for 3 species would finally lay the sterile neutrino anomalies to rest, confirming the standard model in a spectacular way. But if the energy density were even a fraction higher, it would be a monumental discovery, providing the first direct evidence for a particle that has been hiding in plain sight for 13 billion years. A particle that could be a portal to understanding dark matter and the unification of all forces. But if the ghostly nature of neutrinos makes direct detection a monumental challenge, our 7th mystery asks what we might actually see if we could finally map this ancient sea. We know the cosmic microwave background is not perfectly uniform. It's adorned with incredibly faint temperature variations, tiny hot and cold spots that are the seeds of all future structure in the universe. These anisotropies, as they're called, are a fossilized imprint of the quantum fluctuations that were stretched to cosmic sizes during inflation. The logical question, then, is, does the cosmic neutrino background possess its own unique pattern of anisotropies? The answer is almost certainly yes, but the story of these patterns is far richer and more complex, offering a view of the cosmos that the CMB simply cannot provide. The anisotropies in the CNUB would be a kind of cosmic palimpsest, a document with multiple layers of history written upon it. The first layer was inscribed in the very first second. Just like the photons, the primordial neutrino sea would have inherited the initial quantum ripples from inflation, but then their story diverges dramatically. The photons were trapped in the hot plasma for hundreds of thousands of years, their paths scrambled by constant collisions with electrons until the moment of recombination set them free. The neutrinos, having decoupled just 1 second after the Big Bang, embarked on their journeys almost immediately. This means that for those first several 100,000 years, while the photons were stuck, the neutrinos were streaming freely across the expanding universe. And as they traveled, they began to feel the subtle, growing pull of gravity. This is where the second, and perhaps most important, layer of the CNUB's anisotropy was formed. The initial quantum ripples represented tiny variations in density. Over time, gravity acted on these variations, causing the slightly denser regions to pull in more matter, both dark and ordinary. As these gravitational wells began to form, they affected the neutrinos passing through them. A neutrino flying directly toward a developing overdensity would lose a tiny amount of energy as it climbed out of the gravitational potential, causing it to appear slightly colder. Conversely, a neutrino flying away from such a region would gain energy, appearing slightly warmer. This effect, known as the Sachs-Wolf effect for neutrinos, would have started imprinting a pattern on the cosmic neutrino background from a much earlier epoch than the same effect could imprint on the cosmic microwave background. While the CMB's anisotropies largely reflect the state of the universe at 380,000 years, the CNUB's patterns would encode a dynamic movie of gravitational structure formation that began when the universe was only seconds or minutes old. It would be a direct map of the universe's gravitational toddler years. This leads to the immense challenge and the even greater reward. Detecting these anisotropies is exponentially harder than mapping the CMB's fluctuations. The CMB photons have energies that correspond to a temperature of around 2.7 Kelvin, which is squarely in the microwave band, a range we can detect with incredible precision using space-based telescopes like Planck. The CNUB neutrinos, however, are ultra-relativistic but incredibly cold, with energies billions of times lower than the neutrinos we typically detect from the Sun. Their expected anisotropy signal is an almost imperceptible whisper of a variation on top of an already near undetectable background. Our current technology simply has no way to measure such a faint, low-energy pattern. Yet the scientific payoff for achieving this feat would be nothing short of revolutionary. A map of the CNUB anisotropies would be more than just a picture. It would be a functional chart of the universe's total gravitational potential across an immense span of cosmic time. Because neutrinos respond only to gravity on these large scales, their distribution would not be biased by the complex physics of gas pressure, star formation, or magnetic fields that complicate the distribution of ordinary matter. It would be a pristine tracer of the underlying dark matter skeleton of the cosmos, and it would show us that skeleton at a time when the largest structures were just beginning to assemble. Comparing this ancient neutrino map with the later photon map from the CMB would allow cosmologists to track the growth of cosmic structure with unprecedented precision, testing our theories of gravity and the nature of dark energy in a completely new way. It would be like comparing a blueprint of a city's foundations with an aerial photograph taken after the city was built, revealing the entire process of construction in between. Now we venture into perhaps the most speculative and thrilling of all the mysteries surrounding the cosmic neutrino background, the possibility that this ancient sea of particles holds the first direct clue to the identity of dark matter. For decades, we have known that dark matter exists. We see its gravitational pull holding galaxies together and shaping the cosmic web on the largest scales. Yet, despite making up about 85% of all the matter in the universe, we have no idea what it actually is. It does not emit, absorb, or reflect light, and it seems to ignore the electromagnetic and strong nuclear forces completely. It is the universe's ultimate ghost, felt only through its gravity. But what if it isn't completely silent? What if dark matter particles, whatever they may be, can actually interact with something other than gravity? The cosmic neutrino background might be the one medium that could carry their whisper. This idea rests on a simple but profound question: do neutrinos talk to dark matter? In our current standard model, they don't. Both are famously aloof particles, but many theories that seek to explain dark matter propose the existence of a dark sector, a hidden realm of particles and forces that operates alongside our own but interacts with it only very weakly. In these models, it's possible that dark matter particles could interact with normal matter through a new yet undiscovered force. And if that's the case, neutrinos, being the most abundant massive particles in the universe after photons, would be the perfect messengers. Among all neutrinos, the relic neutrinos of the CNUB are the ideal candidates for this interaction because they have been present since the beginning, bathing the entire cosmos, including every clump of dark matter for all of time. So, how could such an interaction leave a mark? Imagine a vast cloud of dark matter, like the halo surrounding our own Milky Way galaxy. For 13.8 billion years, the cosmic neutrino background has been flowing through this halo. If dark matter particles are completely inert, as our simplest models assume, then these neutrinos would pass through untouched, like ghosts through a wall. But if there is even a minuscule chance for a dark matter particle to scatter off a relic neutrino, to give it a tiny nudge, the cumulative effect over billions of years would be significant. This scattering would not happen often. It would be an incredibly rare event, but across the immense scales of space and time, it would leave a specific, detectable signature on the distribution of the neutrinos themselves. The signature would be a subtle distortion in the CNUB's anisotropy pattern, a kind of blurring or smoothing effect. As relic neutrinos streamed through regions of high dark matter density, those rare scattering events would slightly redirect their path. This would cause the neutrino hot and cold spots we discussed earlier to be less sharp, less defined than they would otherwise be. It would be like looking at a pattern through a slightly foggy window. The amount of blurring would directly tell us about the strength of the interaction between dark matter and neutrinos. A direct detection of the cosmic neutrino background that revealed this kind of smoothing would be a revolutionary breakthrough. It would be our first ever piece of evidence that dark matter interacts with anything via a non-gravitational force. This would immediately rule out a whole class of dark matter candidates, like WIMP or actions that are completely non-interacting, and point us toward more complex models. The implications of such a discovery would be staggering. It would open a window into the dark sector, giving us our first experimental handle on the physics of dark matter. We could begin to ask questions we can only dream of today. Does dark matter have its own internal structure? Does it feel forces analogous to our own electromagnetism? The strength of the interaction measured from the CNUB distortion would provide a crucial number for theorists to plug into their equations, constraining the mass and cross-section of the dark matter particle. This single observation could transform dark matter from a purely gravitational phenomenon into a tangible particle with properties we can actually study, setting the stage for a new era of particle cosmology. The cosmic neutrino background, a fossil from the first second, might just be the key to illuminating the dark 85% of our universe that has remained hidden since its creation. Shifting our gaze even further back in time, beyond the first second and into the very first fraction of a second, we confront a mystery that connects the largest scales of the cosmos to the smallest scales of quantum mechanics. This is the profound link between the cosmic neutrino background and the theory of cosmic inflation. We have strong evidence that the universe underwent a period of hyper-fast, exponential expansion when it was only a tiny fraction of a second old. This inflationary burst is believed to have taken the microscopic quantum jitters of spacetime itself and stretched them into the macroscopic density variations that would later become galaxies. The cosmic microwave background provides our primary evidence for this, displaying a pattern of hot and cold spots that align perfectly with inflationary predictions. But the CNUB, being a fossil from a far earlier time, might hold an even more pristine and revealing record of this primordial event. To understand why, we need to appreciate the journey of information in the early universe. The quantum fluctuations generated during inflation are the seeds of all structure. These seeds are imprinted on every particle species present at the time. However, as the universe evolves, those initial imprints can get blurred or overwritten by later physical processes. The photons that make up the CMB underwent a turbulent history. For hundreds of thousands of years, they were trapped in the hot plasma, constantly scattering off free electrons. This process, known as silk damping, effectively erased the inflationary information on very small scales. Think of it like a photograph that was developed and then repeatedly copied. Each copy loses a bit of fine detail. The CMB is an excellent picture, but it's a copy of a copy, with some of the finest grained information from inflation lost. The relic neutrinos, by contrast, had a much cleaner journey. They decoupled from the cosmic plasma a full second after the Big Bang, which is still incredibly early, but more importantly, once they were essentially free forever. They did not experience the same scattering and damping that the photons endured during the subsequent several 100,000 years. This means the pattern of anisotropies in the cosmic neutrino background would be a much more direct transfer of the initial inflationary blueprint. It would preserve the details of those quantum fluctuations on scales that were completely washed out in the photon background. If we could read this neutrino map, we would be looking at a higher resolution version of the universe's birth certificate, one with finer print that we've never been able to decipher before. This enhanced resolution is the key to unlocking new physics. The specific statistical properties of the inflationary fluctuations, their strength across different scales, their distribution, are determined by the physics of the inflationary field itself, often called the inflaton. Different models of inflation, which postulate different types of inflaton fields and potential energies, make different subtle predictions for this pattern. The CMB data has already ruled out many simple models, but the remaining contenders often make predictions that are nearly indistinguishable at the scales probed by the CMB. The CNUB, however, would probe a much wider range of scales, including those that correspond to physics at energy scales 1 trillion times higher than what the Large Hadron Collider can achieve. Detecting a slight deviation from the simplest inflationary models in the CNUB's pattern could be the clue that points us toward the correct theory of everything, potentially linking inflation to string theory or other quantum gravity models. The faint whisper of the cosmic neutrino background might be the only way to hear the echoes from the highest energy regimes the universe has ever experienced. While we often speak of the moment of neutrino decoupling as a single, defining event in cosmic history, the reality is far more nuanced and scientifically rich. This brings us to our 10th mystery, which asks not just when the neutrinos broke free, but precisely how that process unfolded. Our standard models place this pivotal transition at roughly 1 second after the Big Bang, but to simply state this as a fact is to miss a profound opportunity. The exact timeline of decoupling is not a fixed number written in stone. It is a sensitive probe, a cosmic clock that ticks to the rhythm of the fundamental laws that govern the universe in its fiery infancy. Imagine the universe in that first second. It is an unimaginably dense and hot soup of particles, protons, neutrons, electrons, photons, and neutrinos, all constantly colliding and interacting. At these incredible energies, neutrinos are not the ghostly passers-by we know today. They are active participants tightly coupled to the cosmic plasma. They are being created and destroyed in energetic collisions, but the universe is expanding at a ferocious rate, and as it expands, it cools. The critical moment arrives when the average energy of the particles drops below the threshold needed to easily create new neutrino-antineutrino pairs. At this point, the creation of new neutrinos effectively stops. However, the existing neutrinos are still bumping into other particles. True decoupling, the moment when neutrinos cease interacting altogether and begin their endless free-streaming journey, is not an instantaneous switch. It's a gradual process, like a fog slowly lifting. The rate of collisions decreases as the universe becomes less dense, until the typical neutrino will travel a distance greater than the observable size of the universe at that time without a single collision. That is the point of no return. Why does the precise timing of this fade-out matter so much? Because it depends critically on the interaction rate of neutrinos with the rest of the plasma. And that interaction rate is dictated by the fundamental properties of the weak nuclear force. Our current calculations are based on the standard model of particle physics. If the standard model's description of neutrino interactions is perfect and complete, then the decoupling should have unfolded on a very specific schedule. But what if there were other players on the field during that first second? The presence of any unknown, lightweight particle species would have increased the energy density of the early universe, causing it to expand at a slightly different rate. A faster expansion would have cooled the plasma more quickly, potentially hastening the decoupling process. Conversely, a new, subtle interaction between neutrinos and other particles, perhaps even dark matter, could have kept them entangled with the plasma for a fraction of a second longer. This is where the cosmic neutrino background becomes our most precise chronometer. The properties of this relic sea are a direct snapshot of the universe at the moment the neutrinos broke free. A key observable is the precise spectrum of the background, the distribution of energies among the neutrinos. During the decoupling process, as the universe cooled, the neutrinos were not perfectly isolated. They were still weakly interacting with the electrons and positrons in the plasma. Just before the electrons and positrons annihilated away, they transferred a tiny bit of their heat to the neutrino sea. If decoupling were instantaneous, this energy transfer would not have occurred. But because it was a gradual process, the neutrinos did receive a small, calculable amount of heating. The exact shape of the CNUB's energy spectrum is exquisitely sensitive to the duration of this decoupling epoch. A direct measurement of that spectrum would allow us to rewind the tape and determine, with phenomenal accuracy, exactly how long it took for the neutrino fog to lift. Pinpointing this cosmic milestone would do more than just satisfy our historical curiosity. It would place incredibly tight constraints on any physics that operates beyond the standard model. For instance, many theories that seek to explain dark matter or the matter-antimatter asymmetry predict the existence of new, very light particles or new forces that would have been active in the early universe. These would have left an imprint on the decoupling process. A measurement of the CNUB spectrum that perfectly matches the standard model prediction would powerfully rule out a wide swath of these theoretical possibilities. However, a deviation, no matter how slight, would be a smoking gun. It would be direct evidence that something beyond our current understanding was influencing the physics of the cosmos during its very first second of existence. The time of neutrino decoupling is therefore not just a date. It is a fundamental test of our most basic assumptions about how the universe worked at its inception. The formation of the universe's grand architecture, the vast cosmic web of galaxies and clusters we see today, is a story written by the interplay of dark matter, ordinary matter, and gravity. But there is a subtle yet crucial character in this story that is often overlooked: the sea of relic neutrinos. Their role forms our 11th mystery, asking how these elusive particles actively shaped the largest structures in existence. While dark matter provided the gravitational scaffolding, the cosmic neutrino background acted as a cosmic sculptor, subtly carving away at the blueprint and determining which structures would grow to maturity and which would remain stunted. To understand this, we need to think about gravity and motion. In the early universe, dark matter began to clump together under its own gravity, forming the seeds of future galaxy clusters. Ordinary matter, in the form of hydrogen and helium gas, was pulled into these growing gravitational wells, But neutrinos, with their tiny but significant mass, behaved differently. Because they were born with extremely high speeds, a significant fraction of the speed of light, they were what cosmologists call hot dark matter. For billions of years, these neutrinos have been zipping across the cosmos, and this high velocity gave them a powerful advantage over gravity's pull. When a clump of dark matter tried to gather them in, most neutrinos would simply stream right through the gravitational potential and out the other side without being captured. This phenomenon is known as free streaming, and it had a specific and measurable effect. It suppressed the growth of structure on the smallest scales. Imagine a farmer trying to build a pile of leaves on a windy day. The leaves represent the dark matter. The farmer's raking is gravity trying to gather the leaves together. But the wind represents the fast-moving neutrinos. Every time the farmer gets a small pile started, a strong gust blows the topmost, lightest leaves away. The farmer can still build a large pile eventually, but the smallest, most delicate piles never get a chance to form. In the cosmic context, this means that the very smallest dark matter halos, those that might have given rise to tiny dwarf galaxies, had their growth inhibited by the streaming neutrinos. The gravitational wells simply weren't deep enough to hold onto particles moving that fast. The cosmic neutrino background provides the initial conditions for this entire process. Its density and velocity distribution set the rules for how effective this sculpting would be. A sea of heavier neutrinos would have blown away more of the small-scale structure, while lighter neutrinos would have had a lesser effect. This is not just a theoretical idea. We see its fingerprints in the universe around us. When astronomers run sophisticated computer simulations of cosmic evolution, they find that the models which best match the observed distribution of galaxies and clusters are those that include a specific amount of hot dark matter in the form of neutrinos. The simulations that ignore this effect predict far more small galaxies than we actually see. The cosmic neutrino background, therefore, is the missing ingredient that makes our simulations align with reality. Its presence resolved a long-standing puzzle in cosmology, explaining why the cosmic web looks the way it does. But this also makes the CNUB a powerful tool for measurement. By precisely mapping the large-scale structure of the universe, counting galaxies and measuring the voids between them, we can effectively weigh the neutrino. The degree of suppression on small scales tells us the combined mass of all three neutrino species. This is how we have already placed some of the tightest upper limits on neutrino mass, confirming that while they have weight, it is incredibly small. Understanding this sculpting role is absolutely key to modeling the universe correctly. Any discrepancy between our predictions and observations of the cosmic web could point to physics beyond our current models. For instance, if we were to find that structure is even more suppressed than our models with standard neutrinos predict, it might hint at the existence of additional, even faster moving particles in the early universe. Conversely, a different pattern of suppression could reveal details about the neutrino mass hierarchy itself. The gravitational influence of the cosmic web also works in reverse. Just as the web shaped the distribution of neutrinos by allowing the fastest to escape, the neutrinos themselves, through their collective gravity, influenced the growth of the web. This intricate gravitational dance, which has been ongoing for over 13 billion years, is encoded in the relationship between the galaxy distribution we see today and the cosmic neutrino background that permeates it. Unlocking this relationship fully requires a direct detection of the CNUB, allowing us to see both partners in this cosmic tango and finally understand how the universe's lightest massive particles helped carve its most massive structures. This leads us to a mystery that strikes at the very identity of the neutrino, a question so fundamental that its answer could redefine our understanding of matter itself. Are neutrinos unique among all the particles of matter? To understand this, we need to look at the antimatter counterparts of other particles. An electron has an antiparticle called the positron. They have the same mass but opposite electric charge. If they meet, they annihilate. This is true for quarks and muons as well. But neutrinos are different. They are electrically neutral. They carry no charge. So, what distinguishes a neutrino from an antineutrino? For decades, we assumed there must be some other quantum property that sets them apart. But a revolutionary idea proposed by the physicist Eta Majorana back in the 1930s suggests something astonishing. What if there is no difference? What if the neutrino is its own antiparticle? This possibility of neutrinos being Majorana particles is one of the most profound open questions in physics. For all other fermions, the particles that make up matter, the distinction between particle and antiparticle is clear and necessary. But for the neutral neutrino, the mathematics allows for a reality where the antineutrino is not a distinct entity, but simply a different spin state of the neutrino itself. Think of it not as a separate coin, but as the same coin showing either heads or tails. If this is true, it would mean that a neutrino could, in a sense, annihilate with itself under the right conditions. This isn't just a philosophical curiosity. It would permit a hypothetical nuclear process that has never been observed, neutrinoless double beta decay. Imagine the nucleus of a certain unstable atom. In normal radioactive beta decay, a neutron turns into a proton, emitting an electron and an antineutrino. But some atoms can't decay by a single beta decay. They require two neutrons to transform simultaneously in a process called double beta decay, which emits two electrons and two antineutrinos. Now, if the neutrino is a Majorana particle, something magical could happen inside the nucleus. What if the antineutrino emitted by the first neutron was immediately reabsorbed as a neutrino by the second neutron? In this scenario, only the two electrons would escape. The neutrinos would never leave the nucleus. This is neutrinoless double beta decay, and detecting it would be the ultimate proof that neutrinos are their own antiparticles. Experiments deep underground all over the world are searching for this incredibly rare event, but so far it remains elusive. The implications of a Majorana nature for the neutrino are staggering, and they connect directly back to the mystery of our existence. Remember leptogenesis, the theory that neutrinos could be responsible for the matter-antimatter asymmetry. That entire elegant mechanism depends critically on neutrinos being Majorana particles. The heavy, right-handed neutrinos of the early universe would have decayed in a CP-violating way, producing a small excess of leptons over antileptons. But for that process to work, the decays must violate a quantum number called lepton number. In simple terms, the total leptonness of the universe must not be conserved. If a neutrino can turn into its own antiparticle, then lepton number is not a sacred quantity. It can be created or destroyed. If neutrinos are Dirac particles like electrons with distinct antiparticles, then lepton number is conserved and leptogenesis cannot work. The Majorana nature of the neutrino is the essential key that unlocks the door to creating a matter-dominated universe. So, where does the cosmic neutrino background fit into this? While proving the Majorana nature will almost certainly come from a laboratory detection here on Earth, the CNUB offers a unique cosmic consistency check. The properties of the relic neutrino C are deeply intertwined with the physics of the early universe. If neutrinos are Majorana particles, it influences their interaction rates in the primordial plasma during the first second. This, in turn, could leave a subtle imprint on the exact thermal spectrum of the cosmic neutrino background. Furthermore, the success of the leptogenesis mechanism, which a Majorana nature enables, would have directly shaped the neutrino asymmetries that might be frozen into the CNUB. If we one day detect the background and find its properties align perfectly with the predictions of a Majorana-based cosmological model, it would provide powerful, independent corroboration from the cosmos itself. It would mean that the story written in the first second of time is consistent with the story we are trying to read in our underground detectors today. The ghostly neutrinos filling the void may already know the answer to this deepest of questions, silently waiting for us to learn how to listen. While we've explored how the cosmic neutrino background connects to dark matter and inflation, our 13th mystery pushes into perhaps the most profound and speculative frontier of all, the quest for a theory of quantum gravity. For over a century, the two pillars of modern physics have stood in majestic but uneasy coexistence. On one hand, we have Einstein's general relativity, which masterfully describes the force of gravity as the curvature of spacetime on the largest scales, the realm of planets, stars, and galaxies. On the other, we have quantum mechanics, which with breathtaking accuracy governs the bizarre, probabilistic world of the atom and its subatomic constituents. The problem is that these two theories are fundamentally incompatible. They speak different mathematical languages and break down when forced to describe the same situation, such as the center of a black hole or the first instant of the Big Bang. Uniting them into a single, coherent framework, a theory of quantum gravity, is the single greatest challenge in theoretical physics. This is where the cosmic neutrino background enters the stage, not as a mere fossil, but as the most sensitive and ancient detector ever conceived. The core of the problem is energy. To see the quantum nature of gravity, we need to probe unimaginably small distances, which requires particle collisions at energies 1 trillion times higher than what the Large Hadron Collider can produce. Such energies were only present in the universe during the first fraction of a second after the Big Bang, a time we can never hope to recreate, or can we? The neutrinos of the CNUB have been traveling for over 13 billion years. Over that immense journey, even the tiniest, most subtle deviation from the known laws of physics could have accumulated into a detectable signal. It's the ultimate example of amplifying a whisper into a shout through the sheer power of cosmic distance and time. One of the key predictions of many quantum gravity theories, such as some versions of string theory or loop quantum gravity, is the violation of fundamental symmetries that we hold sacred. A prime candidate is Lorentz invariance. This is the principle from Einstein's special relativity that the laws of physics are the same for all observers, regardless of their relative motion. It's why the speed of light is constant. Some quantum gravity models suggest that at the tiniest possible scales, the Planck scale, spacetime itself might have a frothy, grainy texture. For a particle traveling across the cosmos, interacting with this hypothetical spacetime foam could be like a long-distance runner crossing a beach of fine sand instead of a smooth track. Over a marathon, the difference in effort is negligible, but over an ultra-marathon spanning billions of light years, the cumulative effect of trudging through that sand could cause a slight, energy-dependent shift in the particle's speed. A high-energy photon might be affected differently than a low-energy one, and a neutrino's behavior might be minutely altered. This would be a violation of Lorentz invariance. The rules of the race would depend on the runner's energy. How would this show up in the cosmic neutrino background? The answer lies in its energy spectrum and its distribution. The CNUB is not a perfectly monoenergetic sea. It has a specific thermal distribution of energies, a relic of its origin in the hot Big Bang. If Lorentz invariance were violated, the propagation of neutrinos across the eons would not be uniform. Higher energy relic neutrinos might have traveled on slightly different paths or arrived with subtly distorted energies compared to their lower energy brethren. This could leave a unique fingerprint on the background, a kind of spectral distortion or an anomalous pattern in its anisotropy that simply cannot be explained by standard physics. Furthermore, because the CNUB neutrinos are the oldest particles we could ever hope to detect, they have had the longest possible time for these minuscule quantum gravitational effects to build up. They have been subjected to the integrated influence of quantum gravity over the entire history of the cosmos. This makes the detection of the cosmic neutrino background a potential experimental test for ideas that are otherwise purely mathematical. It transforms quantum gravity from an abstract philosophical pursuit into an observational science. If we could map the CNUB with exquisite precision and find its properties in perfect agreement with the Standard Model and general relativity, it would place incredibly stringent constraints on quantum gravity models, effectively ruling out those that predict significant Lorentz violation. But if we were to find a tiny, unexplained anomaly, a deviation from the expected pattern that grows more pronounced when considering the vast distances these particles have traveled, it could be our first ever glimpse into the quantum structure of spacetime. The faint signal of the cosmic neutrino background might carry encoded within it the secret of how gravity and the quantum world finally shake hands, offering a window into physics at the very dawn of time. But this brings us to a daunting practical challenge, our 14th mystery, which asks a critical question about the signal we're trying to detect. Is the pristine story of the primordial neutrino background contaminated? We've been speaking of the cosmic neutrino background as a pure, uniform sea from the Big Bang, but the universe has been anything but quiet since that first second. For billions of years, stars have been shining, exploding, and dying, and each of these cosmic events is a factory producing new neutrinos. The signal we are searching for is not alone. It's buried under a fog of astrophysical neutrinos from across cosmic history. Think of it like trying to listen to a very old, very quiet recording of a symphony's first note, but you're sitting in the middle of the concert hall while the entire orchestra is playing the rest of the piece at full volume. The primordial CNUB is that first fundamental note. The noise is the incredible din of neutrinos produced by every star that has ever undergone fusion in its core, every supernova that has ever torn a star apart, and every active galactic nucleus where a supermassive black hole is devouring matter. This creates a diffuse astrophysical neutrino background that fills the entire universe, overlaying the primordial signal. These later neutrinos have a wide range of energies, but crucially, their energy distribution is different from the cold, thermal spread of the Big Bang relics. The neutrinos from the Sun, for example, have specific higher energies. The real challenge comes from the lowest energy neutrinos from distant, ancient supernova, which can have energies that begin to overlap with the highest energy tail of the primordial background. Separating the two is perhaps the most delicate task in all of astronomy. The key to this cosmic forensics work is energy resolution. A future detector capable of seeing the CNUB wouldn't just be counting neutrinos, it would be building an exquisite, high-resolution spectrum of their energies. The primordial neutrinos, having cooled with the expansion of the universe for over 13 billion years, should have a perfect blackbody spectrum, a smooth and predictable curve that is the hallmark of thermal equilibrium. The astrophysical background, however, is a jumble. It's the sum of countless individual events happening at different distances and times. Its energy spectrum would not be smooth, it would be lumpy, with bumps and dips corresponding to the dominant sources of neutrinos at different epochs in cosmic history. By modeling the expected contributions from stars and supernova with extreme precision, cosmologists hope to subtract this astrophysical foreground, much like radio astronomers subtract the static of our own galaxy to see the faint microwave background behind it. The clean thermal signature of the CNUB would then be revealed as the residual, uniform signal that remains after all the other sources have been accounted for. Successfully achieving this separation would be a scientific triumph on multiple levels. First, it would finally give us a pure sample of the Big Bang's neutrino sea. But second, and just as importantly, the astrophysical neutrino background we'd have to subtract is itself a treasure trove of information. It represents the total integrated history of star formation and death throughout the cosmos. Mapping its intensity and energy distribution would provide an entirely new way to census the universe's stellar activity, independent of light-based telescopes. So, the effort to find the primordial signal would simultaneously unlock a new window into the life cycles of stars and galaxies, turning the confounding noise into a valuable signal in its own right. The quest to hear the universe's first whisper forces us to understand every other sound it has ever made. Even though we cannot yet see the cosmic neutrino background directly, it has actually left its signature on another cosmic relic we can observe, the cosmic microwave background. This indirect evidence is our current strongest proof that this ancient sea of neutrinos is real and permeates the cosmos. The connection between these two backgrounds is a beautiful demonstration of how different components of the universe interact through gravity. You see, in the first few 100,000 years, while the photons were trapped in the hot plasma, the neutrinos were already streaming freely. This created a fascinating cosmic tug-of-war that left a permanent mark on the patterns we see in the CMB today. To understand this, picture the early universe as a dense fluid. Within this fluid, there were regions of slightly higher density, the seeds of future galaxies. Gravity tried to pull matter into these regions, increasing their density. However, the intense radiation pressure from the trapped photons pushed back, creating oscillations, waves of compression and rarefaction that moved through the plasma at nearly the speed of sound. These are the cosmic acoustic oscillations, and their frozen imprint is what we see as the hot and cold spots in the CMB. Now, where do the neutrinos fit in? As the fastest-moving particles at that time, the relic neutrinos streamed out of these dense regions much more efficiently than the photons or the ordinary matter could. This rapid exodus had two major effects. First, it slightly altered the gravitational potential wells. The neutrinos, by leaving, reduced the total mass energy in the overdense regions, making the gravitational pull on the plasma a little bit weaker. Second, their free streaming created a kind of gravitational drag that influenced how the acoustic waves propagated. This combination of effects left a specific and calculable imprint on the statistical properties of the CMB, a pattern known as the power spectrum. The most sophisticated space telescopes, like the Planck satellite, have mapped this CMB power spectrum with extraordinary precision. When cosmologists fit their models to this data, they find that the models only match the observations if they include the gravitational influence of the cosmic neutrino background. Specifically, the presence of neutrinos suppresses the power of the temperature fluctuations on very small angular scales. It also affects the precise timing and phase of the acoustic peaks, the harmonic features in the power spectrum. The data from Planck are so good that they don't just confirm the existence of the CNUB, they effectively allow us to count the number of light neutrino species. The result is a resounding confirmation of the standard model. The data are perfectly consistent with there being exactly 3 types of light neutrinos. This is a monumental achievement, proving the presence of an invisible component of the universe through its gravitational footprint on something we can see. However, this success story is not without its intriguing wrinkles. While the overall picture is a stunning confirmation of our standard cosmological model, there are subtle tensions in the data that have captured the attention of theorists. One of the most discussed is the so-called Hubble tension, a discrepancy between the expansion rate of the universe measured from the CMB and the rate measured from nearby galaxies. While neutrinos are not the primary suspect for resolving this tension, their properties are intertwined with the solution. The gravitational effect of neutrinos influences how fast structures form, and this is linked to the inferred expansion history. Some analyses suggest that slight adjustments to the neutrino sector, such as allowing for a slightly larger total neutrino mass or for the existence of an extra sterile neutrino species, could slightly shift the CMB inferred value of the Hubble constant. So far, the data strongly prefer the standard 3 neutrino model, but the persistence of the Hubble tension keeps the door open to the possibility that there might be something more complex going on with neutrinos than our simplest models assume. These remaining discrepancies are not failures of our model, they are its sharpest probes. They are the clues that point toward deeper mysteries in the neutrino sector. The fact that the CMB data can be used to place the world's tightest upper limits on the sum of the neutrino masses is a testament to its power. Planck tells us that the combined mass of the three neutrino flavors must be less than about 0.12 electron volts. That is an incredibly small amount of mass, but we still do not know the exact value. A future, even more precise measurement of the CMB's polarization could narrow this down further, or potentially reveal a definitive signature of neutrino mass. Furthermore, any deviation from the perfect blackbody spectrum of the CMB, or any unexpected patterns in its polarization, could be an indirect signal of interactions between the primordial neutrinos and other unknown particles in the early universe. So, every time we look at the detailed map of the cosmic microwave background, we are also, in a very real sense, reading a faded but legible report on the properties and behavior of the cosmic neutrino background. It is a ghostly hand whose gravitational touch shaped the oldest light we can see. But this entire quest to detect the cosmic neutrino background rests on one critical, unspoken assumption, that the neutrinos created in the Big Bang are still here. What if they aren't? This leads us to a startling and deeply fundamental possibility, our 16th mystery, which asks whether these ancient particles might be unstable. Could it be that over the immense span of cosmic history, the universe's first neutrinos have slowly decayed, vanishing into even more elusive forms of matter and leaving behind only a ghost of their predicted signal? The idea of neutrino decay pushes against our standard model of particle physics, which treats neutrinos as stable, eternal travelers. For most known particles, stability is a consequence of conservation laws. An electron is stable because it is the lightest charged particle. There is nothing lighter for it to decay into while still conserving electric charge. Neutrinos, being electrically neutral, don't have that protection. If they have mass, then it is theoretically possible for a heavier neutrino to decay into a lighter neutrino, but to do so, it must emit something to carry away energy and momentum. What could that be? The most plausible candidate is a very light, hypothetical particle that has so far evaded detection, perhaps a massless goldstone boson, sometimes called a majoran. In this scenario, a tau neutrino, if it is the heaviest of the three, could decay into a lighter muon or electron neutrino, releasing this undetectable majoran in the process. Over trillions of years, such a decay would gradually transform the composition of the cosmic neutrino background. The implications for cosmology are profound. If neutrinos decay, the relic sea we are searching for today would not be the pristine snapshot we imagine. Instead of a sea containing all three neutrino flavors in their original proportions, it could be a depleted background dominated only by the lightest, stable neutrino species. The total energy density of the background would be lower than our models predict, and its character would be fundamentally altered. Searching for the CNUB, therefore, becomes a dual-purpose experiment. A successful detection that matches our predictions would provide the strongest possible evidence that neutrinos are, for all intents and purposes, stable over the lifetime of the universe. But a failure to detect it, or the measurement of a signal that is significantly fainter than expected, could be the first clue that we are wrong, that even these ghostly particles have a finite lifespan. Testing this idea in a laboratory on Earth is virtually impossible. The lifetime of a particle is related to its mass. The heavier it is, the faster it tends to decay. But even for the heaviest neutrino, with a mass of maybe a fraction of an electron volt, the predicted lifetime for decay into a majoran could be staggering, far longer than the current age of the universe. We could never hope to watch a neutrino decay in a detector. The cosmos itself is the only laboratory large enough and old enough to have performed this experiment for us. The 13.8 billion-year journey of the cosmic neutrino background is the ultimate test of stability. By the time these particles reach us, any decay process with a timescale comparable to the age of the universe would have left a clear mark on the surviving population. This connects directly to the puzzle of the neutrino mass hierarchy. The rate and outcome of neutrino decay depend entirely on which neutrino is the heaviest. If the hierarchy is normal, with the electron neutrino as the lightest, then the tau neutrino would be the prime candidate for decay. If the hierarchy is inverted, the situation is flipped, and the electron neutrino could be one of the heavier, unstable ones. Therefore, the detailed properties of a detected CNUB, the relative numbers of each flavor we might infer indirectly through their gravitational effects, would offer a cosmic verdict on both their stability and their mass ordering simultaneously. It's a remarkable feedback loop where one deep mystery helps to solve another. Ultimately, the question of neutrino decay touches on the permanence of the universe's fundamental building blocks. We take for granted that the particles we know are eternal, but the cosmos has a way of surprising us. The possibility that the oldest particles in existence might be slowly fading away adds a new layer of impermanence to the cosmic story. It means that the cosmic neutrino background is not a static fossil, but a dynamic entity with its own history of transformation. Our attempt to capture it is not just an effort to see the past. It is an investigation into the very longevity of matter, a search to determine whether the universe's first messengers are still carrying their original message, or if they have been quietly changing their tune for billions of years. Now we arrive at a mystery that connects the ghostly neutrino to one of the most pervasive yet enigmatic forces in the cosmos: magnetism. Vast magnetic fields weave through the space between galaxies, shaping the flow of gas and influencing the birth of stars. But where do these cosmic magnets come from? This is a major unsolved problem in astrophysics, and a surprising theoretical answer points directly to the physics of the early universe and the potential role of the cosmic neutrino background in a process known as primordial magnetogenesis. The core of the problem is a question of scales. We know how magnetic fields can be amplified and sustained by the motion of charged particles in plasmas, a process called a dynamo. But a dynamo needs a seed field to amplify. It cannot create magnetism from absolute nothingness. So where did the initial minuscule seed fields come from? They must have been generated in the universe's infancy. And one of the most compelling hypotheses involves a subtle quantum phenomenon that could have been triggered by neutrinos. This idea is rooted in a concept from particle physics called the chiral magnetic effect. To grasp this, we need to think about a property of particles known as handedness or chirality. Imagine a particle spinning as it moves. If its spin is aligned with its direction of motion, like a forward spinning football, it's considered right-handed. If it's opposite, it's left-handed. In the incredibly hot, dense plasma of the early universe, an asymmetry could have arisen between the number of left-handed and right-handed charged particles, such as electrons. This imbalance is known as a chiral asymmetry. Now, according to the laws of quantum mechanics, such an asymmetry in a plasma can actually generate an electric current. And as we know from basic physics, an electric current creates a magnetic field. This is the essence of the chiral magnetic effect, a chirality imbalance spontaneously generating a magnetic field. But what could create such a fundamental left-right asymmetry in the first place? This is where neutrinos enter the story with dramatic effect. In the first second after the Big Bang, the universe was filled with not only a hot plasma, but also a tremendous flux of neutrinos and antineutrinos streaming out from their recent decoupling. Crucially, the weak nuclear force which governs neutrino interactions is inherently chiral. It interacts differently with left-handed particles and right-handed antiparticles. If there was any existing asymmetry in the neutrino background itself, a slight excess of neutrinos over antineutrinos, or a preference for one-handedness, The scattering of these neutrinos off the electrons in the plasma could have transferred that chiral bias to the charged particles. The neutrinos, in essence, could have acted as a catalyst, imprinting their own asymmetry onto the plasma and kick-starting the chiral magnetic effect. The result would have been the birth of the universe's very first magnetic fields, fantastically weak and tiny, but present everywhere. These primordial seed fields would then have been stretched and amplified by the subsequent expansion of the universe and by the motions of gas during the formation of galaxies and clusters, eventually evolving into the large-scale fields we observe today. The cosmic neutrino background is central to this story because it is the relic of that primordial neutrino flux. Its properties are a direct record of the conditions that might have made this possible. If this theory is correct, then the specific characteristics of the magnetic fields we see across the cosmos, their strength, their coherence length, their structure should be deeply linked to the properties of the CNUB. A slight asymmetry in the neutrino sea frozen in from the first second could be the ultimate origin of every magnetic field in the universe. Detecting the cosmic neutrino background and precisely measuring its properties could therefore provide the missing link in this cosmic chain of events. If we found evidence for a global neutrino-antineutrino asymmetry, it would strongly support this magnetogenesis scenario. Furthermore, the way these seed fields were generated would have left a unique statistical signature on their distribution, a pattern that might still be faintly imprinted on the magnetic fields within the oldest galaxy clusters. By comparing observations of these ancient fields with predictions from models that include the chiral magnetic effect driven by neutrino scattering, we could test this profound idea. It suggests that the same neutrino physics that might explain why we live in a universe of matter could also be responsible for weaving the invisible magnetic fabric that holds the cosmic web together. This growing conflict between our two most reliable ways of measuring the cosmos brings us to our 18th mystery, a puzzle that strikes at the very heart of modern cosmology. The Hubble tension is more than just a disagreement about a number. It represents a potential crisis, a crack in the foundation of our standard model of the universe. If both measurements are correct, then something fundamental is missing from our understanding of physics. And this is where the cosmic neutrino background steps in, not as a mere spectator, but as a potential key witness that could break the deadlock. The connection lies in how we use the cosmic microwave background to calculate the Hubble constant. The Planck satellite didn't measure the expansion rate directly. It measured the intricate pattern of hot and cold spots in the CMB, which is a frozen record of the universe's state at 380,000 years old. To get from that ancient snapshot to a present-day expansion rate, cosmologists feed the CMB data into a theoretical model, a recipe that includes all the known ingredients of the cosmos: ordinary matter, dark energy, and of course radiation, which includes both photons and neutrinos. This model then simulates 13.8 billion years of cosmic evolution to predict what the Hubble constant should be today. The tension arises because this prediction, based on the pristine early universe, doesn't match what we see when we measure the expansion directly in our local modern universe. The model is, in a sense, over-predicting the amount of expansion that should have occurred. This is where the properties of the cosmic neutrino background become critically important. Neutrinos, despite their tiny individual mass, are so numerous that their combined gravitational influence contributes to the total energy density of the early universe. This energy density directly controls how fast the universe expands in its first few moments. If there were something slightly different about the relic neutrino sea, if its energy density were not exactly what we assume, it would change the starting conditions for our entire cosmic model. For instance, if the cosmic neutrino background had a slightly higher energy density than currently calculated, it would mean the early universe expanded just a tiny bit faster during that crucial first second. This small adjustment to the initial expansion rate would then propagate through the entire 13.8 billion year simulation, potentially lowering the predicted value of the Hubble constant today and bringing it into closer alignment with the measurements from supernova and other local probes. So, what could cause such a change in the neutrino background's energy density? The possibilities are deeply intriguing. One leading idea involves the potential existence of additional, sterile neutrino species, as we discussed earlier. Even one extra light neutrino species would increase the radiation density in the early universe, giving it a stronger push and altering the expansion history in a way that might ease the tension. However, current data from the CMB and Big Bang nucleosynthesis strongly disfavor this simple solution, as it would create other discrepancies. A more subtle possibility involves the neutrino mass hierarchy. The way the three neutrino masses are ordered affects how they behaved as the universe transitioned from being radiation-dominated to matter-dominated. This transition imprints a specific signature on the growth of large-scale structure, which in turn influences the CMB power spectrum. A different mass ordering could, in principle, require a slight recalibration of the other cosmological parameters when fitting the CMB data, which might nudge the inferred Hubble constant. Perhaps the most exciting possibility is that the cosmic neutrino background holds the key to a form of physics we haven't yet discovered. The Hubble tension might be the first observable sign of a new type of relativistic particle that existed only in the very early universe, something that decayed away long before the CMB was formed but whose brief existence altered the expansion rate. Or it could point to a non-standard interaction between neutrinos and dark matter or dark energy, a subtle coupling that modified how the universe evolved. A direct detection of the CNUB would allow us to measure its properties independently, breaking the degeneracies that currently exist in our models. Instead of inferring the neutrino background's influence indirectly through its gravitational effect on the CMB, we would have a direct measurement of its energy density and spectrum. This would act as a fixed point, an anchor in our cosmological model, forcing the other parameters to adjust around it. If the tension persists even after this anchor is set, it would be powerful, direct evidence that we need to revise not just a parameter but a fundamental law. The ghostly sea of Big Bang neutrinos may be silently holding the answer to one of the biggest controversies in science, a living relic waiting to testify in the case of the expanding universe. Moving from the grand cosmic puzzles of the Hubble tension and primordial magnetism, we now turn our attention inward to the very essence of the cosmic neutrino background itself. Mysteries 19 and 20 ask a more intimate question about this ancient sea. What does it actually feel like? What is the true energy distribution of these particles? Grouping these two deeply technical mysteries reveals that the CNUB is not just a simple, uniform fog. Its finest details, the subtle nuances of its spectrum, and the detailed map of its momentum are a hidden language waiting to be decoded. Any deviation from the simplest predictions would be a direct telegram from the universe's first second, signaling physics we have yet to imagine. First, let's explore the concept of a perfect blackbody spectrum. This is a fundamental idea in physics that describes the signature of an object in perfect thermal equilibrium. When something is heated, it emits radiation across a range of wavelengths, but the exact shape of that emission curve depends only on its temperature. The classic example is a kiln heating a piece of pottery. As it gets hotter, it glows first red, then orange, then yellow. The cosmic microwave background has an almost perfect blackbody spectrum, corresponding to a temperature of 2.725 Kelvin. This near perfection is a stunning confirmation that the early universe was a remarkably uniform, hot plasma. The cosmic neutrino background should also possess a blackbody spectrum, but with a crucial difference. Its predicted temperature is a colder 1.95 Kelvin, a relic of decoupling before the electron-positron annihilation warmed the photons. But the critical question is it perfect? The universe is a messy place, and perfect equilibrium is a theoretical ideal. During the brief period of neutrino decoupling, the universe was expanding and cooling rapidly. This means the neutrinos may not have had enough time to perfectly equilibrate before they stopped interacting. Furthermore, after they decoupled, they were not completely isolated. The neutrinos were still faintly interacting with the much hotter plasma of electrons, positrons, and photons through the weak force. Then, a moment later, that plasma underwent a dramatic transformation. Nearly all the electrons and positrons annihilated each other, dumping their enormous energy into the photon field, which is why the CMB is warmer than the CNUB. But this annihilation happened after neutrino decoupling. The neutrinos, already free-streaming, mostly missed this energy injection. However, because the decoupling wasn't an instantaneous switch, there was a slight overlap. A small fraction of the energy from this annihilation could have been transferred to the neutrino sea, creating a tiny, calculable distortion in its otherwise perfect blackbody spectrum. This is not a flaw, it's a feature. The exact shape of this spectral distortion is a hypersensitive probe of the conditions during that chaotic first second. It tells us about the precise timing of decoupling and annihilation, testing our understanding of particle physics under the most extreme conditions imaginable. But the story doesn't end there. Any other process in the early universe that injected energy or interacted with neutrinos could have left its own unique fingerprint on this spectrum. For instance, the decay of hypothetical exotic particles in the first second, or even the evaporation of primordial black holes, could have released energy that subtly heated the neutrino background. A detection of the CNUB that revealed a spectrum in perfect agreement with the Standard Model prediction would be a monumental triumph, confirming our cosmic timeline with incredible precision. However, the discovery of an unexpected distortion, a bump, a dip, or a slight skew in the curve would be revolutionary. It would be an unmistakable sign of new physics, a fossilized record of an event or a particle that played a role in the cosmos's infancy but has since vanished from view. The spectrum of the CNUB is therefore more than a temperature reading. It is a high-resolution scan of the universe's first second of life. This leads us directly into our 20th mystery, which requires us to think in a more complex way about the neutrino sea. We often picture the CNUB as a uniform bath, the same everywhere, but to truly understand it, we must consider its detailed structure in phase space. Phase space is a powerful mathematical concept that combines both the position and the momentum of every particle. Instead of just asking how many neutrinos are here, phase space asks how many neutrinos are here and where are they going and how fast. It's the difference between a weather report that simply states the temperature and a high-resolution satellite map that shows the temperature, wind speed, and direction of every air parcel across a continent. The latter gives you a dynamic, predictive picture of the entire system. For the cosmic neutrino background, the phase space distribution is everything. The simplest model assumes that at the moment of decoupling, the neutrinos were in a perfect Fermi-Dirac distribution, the quantum statistics appropriate for these particles, and that they have been free-streaming ever since. This gives us a baseline prediction, but gravity has been at work for 13.8 billion years. As we discussed, the gravitational pull of dark matter halos and the cosmic web should have subtly altered the paths of these slow, cold neutrinos. This gravitational focusing would have created anisotropies in the neutrino density, but it would also have imprinted a specific signature on their momentum distribution. Neutrinos falling into a gravitational well would gain speed, while those climbing out would lose it. Over cosmic time, this would create complex correlations between where a neutrino is and how fast it's moving. The detailed phase space structure of the CNUB is therefore a three-dimensional movie of the gravitational history of the universe, a record of how every ripple and valley in the cosmic gravitational potential has shaped this primordial sea. Any deviation from the simplest free-streaming prediction in this phase space distribution would be a direct signal of new physics. For example, if neutrinos interacted with each other or with dark matter through a new, very weak force long after decoupling, it would have caused them to relax or scatter, erasing the fine details of the phase space structure and making it appear smoother. This would be like a blurring effect on our high-resolution map. Conversely, the presence of cosmic strings or other topological defects from the early universe could have created sharp, line-like features in the phase space. Measuring this level of detail is, of course, a challenge of almost unimaginable difficulty, far beyond our current capabilities. It would require a detector that could not only sense the sinew B, but also discern the direction and energy of each individual neutrino with incredible precision. Yet the theoretical prize is immense. The phase space distribution of the Cosmic Neutrino Background is the ultimate data set. It contains within it the complete story of the neutrino's journey, from its quantum mechanical birth in the Big Bang to its final arrival at our detector, shaped by every gravitational encounter along the way. Decoding it would allow us to reconstruct the universe's gravitational field across all of time, offering a profound new test of Einstein's theory of gravity and potentially revealing the hidden interactions of the universe's most elusive particles. Given the monumental challenges we've explored, the quest to directly detect the cosmic neutrino background might seem like science fiction. Yet, this is a frontier where human ingenuity is rising to the occasion, designing technologies that border on the miraculous to finally listen to the universe's oldest sound. The next generation of experiments is being planned with a bold, almost unimaginable goal: to capture a single, pristine neutrino that has been traveling since the first second of time. Leading this charge is a concept like the Ptolemy experiment, a project that embodies both the audacity and the precision required for this task. Ptolemy's strategy is not to wait for a rare collision, but to literally catch a relic neutrino. It proposes using a solid surface coated with a vast quantity of a specific type of atoms like tritium, a radioactive form of hydrogen. In a tritium atom, a neutron can spontaneously turn into a proton, emitting an electron and an antineutrino. This is ordinary beta decay, but here's the revolutionary idea. If a relic electron neutrino from the Big Bang happens to be passing through the detector at that exact moment, it could be captured by the transforming nucleus. This capture would provide a tiny bit of extra energy to the reaction. Instead of just an electron and an antineutrino, the decay would produce only an electron, but one with a slightly higher, very specific amount of energy. The entire detection scheme hinges on measuring this minuscule energy spike with near absolute precision. The challenge is almost beyond comprehension. The detector would need to be exquisitely shielded from any background radiation, and it would have to analyze the energy of countless electrons to find that one in a trillion event that signals the capture of a primordial ghost. It's like trying to hear the gentle pluck of a single harp string from inside a roaring heavy metal concert. Beyond these direct capture methods, other futuristic concepts are emerging from the realms of advanced quantum physics. Imagine detectors that don't rely on massive volumes of material, but on the exquisite sensitivity of quantum states. Quantum sensors, which exploit the strange properties of superposition and entanglement, could detect the infinitesimal disturbance caused by a passing relic neutrino. A neutrino, while barely interacting, does have a tiny magnetic moment. In theory, as it passes through a carefully prepared quantum system, it could impart a minuscule kick, a quantum flutter that could be amplified and measured. These sensors would operate at temperatures near absolute zero, where quantum effects dominate, turning the entire detector into a single, hypersensitive ear attuned to the quietest vibrations in the cosmos. Another mind-bending proposal looks not at the neutrinos themselves, but at their collective gravitational shadow. We've discussed how the cosmic neutrino background's gravity shaped the CMB, but its influence continues to the present day. This sea of particles, while diffuse, has a total mass that contributes to the gravitational field of the universe. As the Earth moves through space, it is constantly passing through this neutrino sea. In theory, this motion through a medium with mass should create a faint, anisotropic gravitational field, a kind of neutrino wind, that ever so slightly alters the local strength of gravity. Detecting this effect would require measuring variations in gravity with a precision that is currently science fiction, perhaps using networks of ultra-precise atomic clocks or future gravitational wave observatories. It would be an indirect detection, but a profound one, proving the sea's existence through its gentle gravitational tug. Each of these technological pathways represents more than just an engineering marvel. They are windows into different aspects of the CNUB. A direct capture experiment like Ptolemy would give us a pure sample of a relic neutrino, allowing us to measure its energy and mass directly. A quantum sensor might map the local flux and direction of the background, revealing its anisotropies. A gravitational measurement would confirm its large-scale distribution and total density. Together, they would provide a complete picture of this ancient relic. The journey to build these machines is itself a driver of innovation, pushing the limits of material science, cryogenics, and quantum computing. The race to detect the cosmic neutrino background is not just about answering old questions. It is about building the tools that will define the next century of astronomy, tools so sensitive they will undoubtedly discover phenomena we haven't even begun to imagine. The faint whisper of the Big Bang is compelling us to invent a new way of seeing the universe. Beyond the intricate calculations and the formidable technical challenges lies a mystery that transcends physics, touching upon the very nature of our place in the cosmos. To finally detect the cosmic neutrino background would be more than a scientific triumph. It would be a profound philosophical event, reshaping our relationship with the universe and time itself. Consider the journey of a single relic neutrino now passing through you. It was born in the unimaginable fury of the Big Bang's first second, a witness to an era when the fundamental forces were one. It streamed freely as the first protons and neutrons formed, flew through the dark ages before the first stars ignited, and witnessed the entire grand narrative of cosmic evolution unfold, all without ever interacting, a perfect silent observer. To capture such a particle is to hold an artifact of creation, a fossil that makes the ancient universe tangibly, physically present in a way that nothing else can. The cosmic microwave background already gives us a powerful sense of connection to the past. Its map is a photograph of the infant cosmos, a snapshot we can point to and say, this is what everything looked like 380,000 years after the beginning. But the CNUB is different. It is not a photograph, it is a living, breathing relic. It is the universe's first breath, frozen in time and still filling the vastness of space. Detecting it would be like listening to a recording of that first breath, a direct sensory experience of the moment existence as we know it began. This transforms cosmology from a historical science where we piece together clues from the past into something more immediate. The Big Bang ceases to be an abstract, singular event that happened long ago and becomes an ongoing phenomenon, a continuous background hum of creation that has been present every moment since, and one that we are only now learning to hear. This tangible connection to the origin of everything forces us to confront deep questions about reality and observation. In quantum mechanics, the act of observation is often thought to play a role in defining reality. For over 13 billion years, the cosmic neutrino background has existed, a sea of particles in a state of pure, unobserved potential. What does it mean for humanity, a conscious species on a tiny planet, to finally turn our instruments toward this background and, in a sense, observe the universe observing itself at its birth? It suggests a universe that is not only comprehensible but also eager to reveal its secrets, a cosmos that has preserved its own origin story in a medium so delicate and elusive, waiting for an intelligence sophisticated enough to decode it. This moves the needle from simply discovering facts about the universe to participating in a cosmic story of revelation, where our quest for knowledge becomes a meaningful part of the universe's own unfolding narrative. Furthermore, the detection of the CNUB would represent the ultimate validation of the scientific method itself, every step in the chain of reasoning that predicts its existence, from the theory of the hot Big Bang to the standard model of particle physics and the principles of general relativity, is a human construct, a model built from mathematics and observation. To find exactly what these models predict, a sea of neutrinos at 1.95 Kelvin would be a staggering confirmation that the human mind can indeed grasp the logic of the cosmos, even its very first moments. It would mean that the laws of physics as we understand them are not just local bylaws applicable to our corner of the universe, but truly universal and eternal, holding sway from the first instant to the present day. This unity of physical law, stretching across 14 billion years, offers a powerful sense of cosmic order and intelligibility. Yet this very success also highlights our profound solitude. This fossil universe has been streaming through space for eons, bathing countless worlds that may have existed long before our own. As we reach out to touch this ancient signal, we are confronted with the silence of the cosmos. Are we the first to accomplish this feat, or are we latecomers to a conversation that has been ongoing for millions of years? The detectable fossil universe is both a bridge and a mirror. It connects us directly to our origins, but in doing so, it reflects back our own singular responsibility as the only known consciousness capable of appreciating the grandeur of the story it tells. It makes the universe feel intimately close while simultaneously underscoring our unique and fragile place within it. And so we reach the final and perhaps most humbling mystery of all, the one that encompasses every other question we've asked. After exploring 24 profound puzzles, from detection and mass to dark matter and quantum gravity, we are forced to acknowledge that the ultimate secret of the cosmic neutrino background is the one we cannot yet articulate. The greatest lesson from the history of science is that every time we build a new instrument to peer deeper into the cosmos, we don't just find answers to our existing questions, we discover entirely new realities that shatter our previous understanding. Galileo's telescope didn't just reveal more detail on the moon, it showed moons orbiting Jupiter, proving that not everything revolved around the Earth. The discovery of the cosmic microwave background wasn't just a confirmation of the Big Bang, it was the birth of modern precision cosmology, and the detection of dark energy didn't answer a lingering question. It unveiled a force dominating the universe's fate that we never knew existed. The cosmic neutrino background is poised to be the next great revelation of this kind. We have our list of 25 mysteries, a catalogue of profound, known unknowns. But the true revolution will likely come from the unknown unknowns, the phenomena, the particles, the forces that our current theories are simply not sophisticated enough to predict. Our models are brilliant, but they are built on the physics we have discovered within our own limited cosmic epoch. The CNUB is a messenger from a time when the energy scales were 1 trillion times higher than anything we can create in a particle collider. It is entirely plausible that the conditions of the universe's first second gave rise to physical processes that have long since faded from view, leaving their imprint only on the particles that escaped at that very moment. Imagine a future where we have finally built a detector capable of capturing the faint signal of the relic neutrinos. After the initial triumph, the data begins to stream in. Perhaps the spectrum shows a distortion that no model of standard decoupling can explain, hinting at a brief, violent interaction with a field that vanished nanoseconds after the Big Bang. Or maybe the anisotropy map reveals patterns that don't align with any known inflationary model, suggesting a more complex origin story for the cosmos itself. It could even be that the signal contains a component that simply shouldn't be there, a population of particles with properties that defy the standard model, a relic from an era before the forces of nature as we know them had even separated. This is the breathtaking potential of this quest. The discovery of the cosmic neutrino background might not be a quiet confirmation of our existing theories, but a loud and clear announcement that our picture of the universe is fundamentally incomplete. It could be the key that unlocks the door to a theory of everything, not by gently fitting into our current framework, but by breaking it open to reveal a deeper, more elegant structure beneath. The ghostly whisper from the beginning of time may not be speaking the language we expect. Learning to listen to it won't just solve our current mysteries. It will undoubtedly teach us to ask entirely new kinds of questions, guiding humanity toward the next great paradigm shift in our understanding of reality. And so, our journey through these 25 profound mysteries brings us full circle, back to that astonishing reality we began with. Trillions of these ancient ghost particles are streaming through you, through the room you're in, through our entire planet at this very moment. They are the cosmic neutrino background, and they are not merely a scientific curiosity. They are a living, breathing relic from the universe's very first second of existence. We have explored the monumental challenge of their detection, a feat that pushes technology to its absolute limits. We have grappled with the question of their mass and the cosmic implications of their hierarchy, a puzzle that could rewrite the standard model of particle physics. We have seen how this fossil sea could hold the key to the universe's matter-antimatter asymmetry, perhaps explaining our very existence, and how it might reveal the identity of dark matter or even provide our first glimpse into the quantum nature of gravity. From sculpting the cosmic web to seeding the universe's magnetic fields, and from testing the physics of inflation to potentially revealing unstable particles, the secrets locked within this faint whisper are the key goals for 21st century physics. Unlocking these mysteries is more than just filling in blanks in a textbook. It is an active process of discovery that will redefine our understanding of reality. Each question we've asked, from the seemingly simple, "How cold is it?" to the deeply philosophical, "Is it still here?" represents a frontier where our current knowledge meets the unknown. The pursuit of the cosmic neutrino background is a testament to human curiosity and ingenuity, a quest to build instruments so sensitive they can listen to the echo of the Big Bang itself. The answers we find may confirm our most elegant theories, or they may shatter them, leading us toward a new, more profound comprehension of the cosmos. This is the thrilling nature of fundamental science. The journey is as important as the destination. As you go about your day, I encourage you to simply pause and marvel at this incredible fact. You are constantly bathed in a sea of particles that are older than the atoms that make up your body, older than the sun, older than the Milky Way galaxy itself. Each one is a messenger from the dawn of time, carrying a story 13.8 billion years in the making. The effort to read that story is one of the greatest adventures in human history, and it is unfolding right now in laboratories and universities around the world. I urge you to follow along. Keep an eye on the latest news from projects like Ptolemy and other next-generation experiments. The day we finally capture a direct signal from the cosmic neutrino background will not just be a headline for scientists, it will be a milestone for all of humanity, a moment when we reach across the vastness of time and touch the very beginning of everything.